Evening. I have a fairly quick one. It's an inequality that ends up being a fairly sharp inequality. I think it's pretty close. The left-hand side is very, very close to being equal to the right-hand side. Now, the result I'm using, and I'm not sure what all is available. There's plenty of inequality results out there. Jensen's theorem, Holder inequality, but the Cauchy Schwarz inequality fits this one very nicely, I thought. Now, so we're actually looking at this. If you take a look at this statement right here, this summation notation, if you were thinking of A sub I and B sub I as just being sequences of real numbers, this really just says the square or vectors, where these are the components of the vector. This just says the square of the inner product is always going to be less than or equal to the product of the magnitudes squared of the vectors. So that's what it says if you want to think about it from a vector, just purely a vector point of view. But otherwise, we're just going to kind of apply it blindly right here. And now, so in this particular case, n equals to 3, right? And that's because we definitely have 3 sum n's right here, right? So n is equal to 3. And sometimes it's tricky. You have to play one trick. You have to do splits. You have to do all kinds of things. But this one is very, very direct. By the laws of radicals, you can split the radicals apart like this. And notice that's in keeping with, your a sub i's will always be 1/13 here. 1 over the square root of 13, excuse me. So this would be a1 right here, a sub 1, b sub 1. Okay, and this would be a sub 2, b sub 2, second product here. And our third product will be a sub 3, b sub 3. Now, once you get used to it, and it's taken me a while to get used to Cauchy's. I just can't, get the hang of it, it seems like. But if you write it down, you start noticing, what's going on here. So again, these would serve the roles of a sub 1, b sub 1, a sub 2, b sub 2, and a sub 3, b sub 3. And so this would, if you come down here, that would be the left-hand side of this inequality. Okay, that would be, without the summation notation, this would be the left-hand side of the inequality. Notice that it's squared. Okay, now, so since all of the a sub i's or the square root of 13, when you square those individually, you just get 1 over 13, 1 over 13, 1 over 13. That's 1 over the square root of 13 squared. And of course, right here, we have the square root of 10, square root of 9, square root of 7. When you square those numbers, you get 10 plus 9 plus 7. Okay, so there's 3 of these. There's 3 of the 1/13. This adds up to 26. 3 times 26 is 78. And 78 divided by 13 is 6. And notice that's the square of what we're looking for. Okay, remember, this is the object. We're trying to find an upper bound for this guy right here. It is equal to this, all right, but we've gotten it squared down here. So if you take the square root of the inequality, of this inequality, you get the result that we were trying to show. So we're done with that, folks. Now, by the way, I did want to say this, I think it's pretty sharp. If you check your calculator on this, I think it's very, very close, these two things, like within thousandths of each other. But the only way the equality condition holds would be if the a sub i's and the b sub i's were scalar multiples of each other. Or another way of putting that, if you have a sub I over b sub I, all of them, this would be I equals 1 to 3. I'll just write it in the index form here. If these were all equal to some scalar, okay, then that's when you would have equality. That's when you would have equality. I don't have any numerical example, but another way of putting this, if a sub I is a scalar multiple of b sub I, then you would have the equality part of this would hold. But that's clearly not the case right here. Root 10 over root 13, I don't know the numbers, but you can tell they couldn't be the same ratios, right? Root 10 over root 13 is going to be a different scalar than root 9 over root 13. So that's not going to happen. And so you could actually lift this equality condition right here. We proved it just, but that equality, in other words, this really is a strict inequality. I didn't rigorously show it, but hopefully the argument there suffices. This is definitely a strict inequality. So anyway, y'all, Nice application of Cauchy Schwarz, or not an application, but just a numerical example of it. Thanks for viewing.